Hello, everyone. My nickname is Victor V, and I'm excited to share my research finding with you all. Let's dive into our topic, unveiling the cracks in virtualization, mastering the host system, VMware Workstation escape. First, let me introduce myself. Here is my Twitter account. I'm from Cyber Kunlun, a company with several world-class security researchers. I mainly focus on binary security research. I completed VMware Workstation escape 3 times in the competition of TianfuCup. I ranked in top 3 of MSRC leaderboard for Q3, Q4 last year. And also, I'm the second top 2 of this year Q1. I also shared my security research at ZeroCon and HitB. In 2021, I completed a Hyper-V escape. In addition of security workstation security research, I also found several well-known products in. I also found several critical or important security bugs in several well-known products. Now, let's briefly summarize the topics we will cover. First, I will introduce some basic information about virtualization to help those who haven't encountered the virtualization escape before. Next, I will discuss historic bugs in UHCI, and both discovered by others and by me. After that, I will use 2 vulnerabilities I used at TianfuCup 2023 as a case study to explain how to exploit virtualization escape. Finally, I will summarize my content to reinforce your understanding. Let's get started. Part 1, virtualization basic info. When it comes to virtualization escape, there are 3 key questions we need to understand. First, how is the virtual machine constructed? Next, how is data transmitted between the guest system and the virtual device? Then, what is the virtualization escape? To address these questions one by one, let's start with the first question. How is a virtual machine constructed? A virtual machine typically consists of a hypervisor and many virtual hardware devices. For VMware Workstation, a part of its hypervisor is run in the kernel, and some parts are run in the user mode process. Most of its virtual hardware devices are implemented in the same user mode process. So this diagram illustrates the software architecture of VMware Workstation. We can see a hypervisor with multiple of virtual hardware devices here. The focus of our discussion today is the USB controller. Next, let's address the second question. How is data transmitted between the guest system and the virtual hardware devices? There are 2 methods. One is by directly reading and writing guest's physical memory. The other is through I/O operations. Here, let's learn the first method. The entire guest's physical memory is mapped as a segment of virtual memory space of VMX process. Guest virtual address, short for GVA, is the address needed by programs in the guest virtual machine. In guest, programs use GVA access its physical memory. Before being passed to VMX process, we need to get the guest physical address of GVA. In the VMX process, it uses host process virtual address, short for HVA, of GPA to access guests with physical memory. The process of converting GPA to HVA is completed in the VMX process. And the guest system and the VMX process can access the same memory at the same time. This is really important. Our operation is the second method. basically, almost all virtual hardware devices are implemented in the user mode process. So the interaction between the guest system and the virtual hardware devices is an interaction with the VMX process. They can directly transfer data through I/O ports and I/O memory. For I/O ports, these CPU instructions are used. For I/O memory, it can be mapped to guest virtual address for directly read and write in guest system. I/O operations are fast, but transfer less data. So for large data, the address converting operation from the previous page is generally used. Next, let's tackle the last question. What is virtualization escape? Let's make a comparison with remote code execution. Virtualization escape and remote code execution have many similarities. In the exploitation of remote code execution, attacker sends data to the server and crack the structure of server process, then get leaked data from receiving messages over network. Then it sends another data to server and control server process RIP, then run ROP to get code execution. So for virtualization escape, the most difference is our transmission of messages is facilitated through the guest's physical memory and I/O operation. So to complete a virtualization escape, arbitrary address read and write are often required. After addressing the key questions, let's begin to explore USB controller. So far, VMware has implemented 3 USB controllers: USB 1 series, known as UHCI, USB 2.0, known as EHCI, USB 3 series, known as XHCI. Perhaps in the future, we can see the implementation of USB 4 series. These are some public known CV numbers for VMware that can be escaped. So interested parties can look into them later. This slide shows the device information of XHCI and UHCI in a Linux virtual machine. As you can see, XHCI uses I/O memory for data transmitting, while UHCI uses I/O port 20C0. This is the device relationship diagram of the UHCI controller. The UHCI controller has 2 default ports. When a device is connected to one port, a hub is needed to expand for new USB devices. This is a USB architecture diagram in a VMware Workstation installed Windows 10 guest system. By default, a virtual Bluetooth and a virtual USB hub are mounted under UHCI. A virtual USB mouse is mounted under XHCI. So, and there is no device mounted under EHCI. And specifically, virtual Bluetooth required host enable Bluetooth. So if you are doing research on a desktop, you may not find my bugs in the further presentation. And if we reject XHCI in the guest system, the USB mouse will be mounted under USB hub. Here is the relationship diagram of message structure transmitted to the UHCI controller. The device driver passes the guest physical address of frame list to the virtual device through I/O operations. The frame list is an array. Each member stores the guest physical address of first QH structure. The QH structure has 2 GPA addresses. pointing to the next QH structure or TD structure. The last two bits indicates whether GPA points to a QH or TD. If the GPA is 0 and the last bit is 1, it means this is the end of the list. The TD structure's first 4 bytes is GPA2. It points to the next TD structure, and the rest of TD structure are data. Here is a simple example of a TD structure. DMLalloc is a function to allocate continuous physical memory that returns GVA to TD and gets the physical address to the second parameter. The frame list array stores the GPA of TD structure and sets the last bit to 1. Here is the TD structure. The TD structure's first integer is set to 1. It means this is the last TD structure. And here it sets device ID, endpoint ID, length of extra buffer, and the TD structure's type through bit shifting operation. And it sets the last integer with buffer of GPA, a GPA of buffer. So when we start to explore a target, we usually begin by understanding its architecture and its implementation. Now that we have already understood its architecture, I will take everyone a historic bug. Inspired by this historic bug, I find a way to bypass some restriction and create a new bug. After further exploration, I find more bugs. Here, let me introduce a historic bug, CVE 2019-5519. It's a timeout check, timeout use bug. It was found by Ahmad and Richard Zhu. They use it at Pontoon. The purple area is the DMA map structure in VMX process. It stores the HVA of TD structure. In the UHCI thread, it reads the length field of TD structure by HVA and calculates the total length of TD structures. Then it allocates URB structure by count length and reads the length field of TD structure by HVA again. So the SVG thread is the implementation of virtual graphics card in VMX process. It can access guest physical memory at the same time. If we use SVG thread to modify the length field of TD structure at the same time, then after the UHCI thread has finished counting the length, when the UHCI thread accesses the TD structure second time, it will read the modified length. So we call that heap overflow. So after analyzing their bugs, I start to reproduce their bugs and do more review of UHCI. Inspired by them, I realized I could bypass a restriction and create a new vulnerability. Let's see how I did. Line 1 to 3 is a while loop. Line 2 is a while loop 2. If this function returns non-zero, it will increase the variable I and continue the loop. Here is the implementation of that function. First, it gets frame index by frame start field and the parameter index. Then it reads the first QH structure's GPA by reading guest physical memory. Then it sets the return value read by frame index value. Here is the while loop. It gets the DMA map structure by GPA. If the GPA has been converted before, this condition will hold. So it will skip the further operations. Here, it gets the endpoint structure by device ID and endpoint ID of TD structure. If endpoint structure type is 1, it will allocate an array to store each TD structure's data. And it uses parameter index as array index. Here, if index is smaller than 4000 or 400, it will set red to 1. So it's obviously when the index is smaller than 400, this while loop will not stop. When the index reaches to 400, if we set frame start to 3FF, the frame index will be 3FF again. This condition will hold, so the red will be 1. However, because frame index start repeat, so the frame list, the GPA of frame list will start repeat. And this condition will hold. It will skip further operations. So we can't overflow map array. So if we compete to modify the value of frame list, then it will get a different value at the second time. So we can overflow map array now, because this restriction will not hold. So in the further vulnerability research, we discovered an information leak in 2021. We were going to use it at TianfuCup 2022. However, the competition was postponed and canceled. And at PointOn 2023, Star Labs used it. So it was patched. What a pity. All right, let's see what the bug is. Here is a URB structure. The C field indicates that the size of data the guest can read from URB's buffer. And this field is pointing to the buffer with some offset. The URB structure is allocated through this function, and the buffer size is decided by this parameter. The URB structure is allocated by malloc, so the information of URB's buffer is not initialized. Here is the function. TD structure is being get out from the map array. If TD structure's type is set up and URB has not been allocated, it will allocate a URB structure with controllable size and set size to the count size field. The count size field is ACE field here. If TD structure's type is output, it will copy data from extra buffer of TD structure to the URB's buffer. If TD structure's type is input, it will do nothing. So if all TD structure's type is input, except for the first one, then TD structure's buffer will not be initialized at all. In the further operation, the virtual Bluetooth device processes the URB structure, and it assigns the value of ACE field to the C field directly, and it won't change it in the further operations. So the guest can read uninitialized memory from URB's buffer. And here is a patch. They add codes under these operations. They set a number 8 to C field for specific conditions. And it's obviously they don't understand what is wrong. They should reset the memory of URB's buffer. So we can trigger this bug in the virtual mouse device. And I use it at TianfuCup 2023. So after discovering so many bugs, I felt certain that there must be more bugs in this module. And upon learning that it was possible to remove XHCI within the guest, I found this bug. It's an UAF bug. In this function, it takes out the next pointer from UHCI main structure's link. If it's not the beginning of the link, it gets the endpoint structure by subtracting variable next. Then it obtains the next member of the link. Later, it handles the control type endpoint in the further operations. In the implementation of Virtual Hub, it can reset the devices mounted under it. The reset operation will free all endpoint structures of mounted devices and reapply a new control endpoint structure to it. Remember the basic UHCI architecture we mentioned before? When we removed XHCI, a virtual mouse is mounted under USB hub. So if the endpoint here is the control endpoint of virtual hub, and the next is the endpoint of virtual mouse, if we reset the mounted devices of virtual hub in the further operation, the endpoint of mouse will be freed. So the variable next will become a dangling pointer. Thus, we caused an UAF bug. So after finding useful bugs, how should we exploit it? Through this practical example, you must be able to exploit bugs more smoothly. In the white paper, straight out of VMware, they mentioned the component for exploiting vulnerabilities. In the SVG device, there's a surface structure. A surface can bind to a mob structure, and the mob structure saves the HVA of GPA. In addition, the surface can bind to a backend structure too, and the backend structure can apply a backend heap. If we let the bug heap and the backend structure into a same LFH segment, if the bug heap can overflow right, if we are lucky, we can overflow the backend structure and change the pointer of backend heap. So through SVG commands, it's possible to copy data between two surfaces. So we have the ability to read and write arbitrary or VMX process heap. If we want to use this component, we just need to find a bug that can construct an out-of-bounds write. The bad news is that this method is no longer effective because the officials saw their report. So they put the backend structure into another process named MKS sandbox. So this method is not valid again. In my speech, breakout script of Westworld, we propose a new method. If the conversion size of mob is 1,000, when the mob tries to convert GPA to HVA, if the conversion fails, it will apply a heap with size 1,000 as HVA. Through SVG commands, it's possible to copy data between two mobs. So we have the same ability again. If we exploit the vulnerability to overflow the length field of surface, then we can out-of-bounds read and write this heap. With some memory arrangement, we can overflow mob structure and change the HVA value. So we can achieve arbitrary address read and write again. And of course, we can overflow mob structure directly because we don't know we don't know an address of VMX process related unless you have an information leak. However, this method also be blocked in VMware Workstation 17. They no longer apply for 1,000 heap for the mob structure, and the mob structure was also put into a large vector, making it more hard to modify. Fortunately, I finally found a way to achieve arbitrary address writing, which is in the function of UHCI for reading data from URB. I cut down unimportant codes. A2 is the endpoint structure. The first gets the URB structure, then gets the endpoint structure again from the URB structure. Later, it gets a pointer from the endpoint structure and gets a value from V8. If this condition is okay, a 4-byte assignment will follow. So if we can control an endpoint structure or URB structure, we can fake V8. Then we can achieve arbitrary address write. The drawback is we must know the value of target address because of this condition. The good news is that I have an information leak, and through UAF, I can control endpoint structure. So with the idea and the vulnerability, let's start the exploitation. In this picture, we use SVG shader structure to do heap spray. And we leave a gap for normal URB structure and put a gap in front of the normal URB. Then we free normal URB and the gap structure. So they will merge. After that, we apply for mouse URB again, making it just right to apply to the merged memory. So with the leaking bug, we can leak the uninitialized memory of mouse URB. So we can leak the normal URB structure's data. Then we can get a URB heap related address by this field, and a VMX process related address by this field. Because endpoint structure is a dangling pointer and belongs to the LFH heap, I compete to modify the value of endpoint through the illustrated method. First, extend the size of LFH segment to the maximum, which is 41FF0. Then prepare as many virtual hub control commands as possible. Each command resetting the endpoint structure of virtual mouse. We use this way to expand the competition time gap. At the same time, we use SVG thread to submit commands to allocate and release the same size heap. In this way, when the UHCI thread accesses the dangling pointer, it's likely to point to the endpoint structure that we control. Thus, we can achieve arbitrary write. The failure possibility of this step is 1 in 40 because the LFH feature. So with arbitrary writing, we modify the current buff field of URB structure. Let it point to the mob table. The mob table stores the mob structure's pointer. And once again, we use UAF bug, modify the mob table. Here, why we let it point to mob table? Because the arbitrary writing need to know the value of target address. Then here, once again, we use UAF vulnerability, modify the mob table to point to SVG global buffer. Mob table is now we can modify the content of SVJ global buffers, so SVJ comments, to fake a mob structure. Then, once again, we leverage the power of mob structure to achieve arbitrary address read and write. Then, you can find a function pointer of VMware process and leak WinExec function address. And you can use WinExec to bypass CFG. So you can execute any commands you want. Here is the demo. First, I check the version in the guest system. And the version of VMware Workstation is 17.5. Then I run a program in the guest. Here is a process tree in the host of VMware process. As you can see, a calc program popped out under VMware process tree. So we can run anything in host now. Finally, let's summarize the knowledge points mentioned earlier. First, vulnerability mining, timeout check, and timeout use. The data of HVA can compete. You should pay attention on this when you do virtualization security research. Next, UAF, notice reset operations. You can check a similar bug, CV 2020-4004. Second, exploitation techniques. First, use URB structure to leak information you want. Even if you don't have an information leak bug, you can overflow URB structure's first field and get an information leak bug. Next, use endpoint structure to achieve arbitrary write. With the power of mob structure, you can achieve arbitrary read and write again. And finally, how to defend against virtualization escape. First, remove unnecessary devices such as USB controller, sound cards, CD-ROM, and disable unnecessary features such as SVJ3D. The component I use for mob structure may need SVJ3D. And last, keep your software newest. This way, it's likely to avoid virtualization escape. You may think, oh, I use an old version, so they can't attack me. Actually, the older version has more escape bugs, so don't use older version. And thank you for your listening. Welcome to your questions. Okay.
Hello, thank you for your presentation, and I would like to hear more about, I see that 2 people are working on finding bugs in your case, you and your colleague, right? And I would like to know the strategy, like how you approach to find the bugs, to escape the virtualization.
Found bugs.
Like, my question, are you fuzzing a lot, or it's more about code review, or when you 2 people working on the to find the bug?
Yes, they found bug in EHSI. The main part of here is do research in different environment. It's very, very important. We lost the bugs I mentioned here, the first history bug, because we do research in desktop PC. They don't it doesn't have Bluetooth, so that proceed function we can't go in, so we ignore it. So we lost 2 bugs. And try do anything abnormal. For example, I remove XHCI in guest. It's really abnormal. If I didn't do this, I don't know USB mouse can mount it on the virtual hub. So the UF bug won't be triggered in default environment. And do review as much as you can. First, there are historic bugs. Then understand hardware architecture by manual. UHCI, Intel has a manual, so you can read how they handle data from guest driver and how they should do in the first operation. So you can learn this by guest driver in Linux system too. They will implement the manual in the guest driver, so you can learn from it too. You should learn the guest driver first before digging bugs in virtual hardware. I think, is that solve your problem?
Yeah, of course.
Okay.
Thank you.
Any question? Okay, that's all. Thank you.